there will be some electrical circuits that we meet which will have a power supply or a battery which has an internal resistance. So what we'll look at here what implications that has for the kind of electrical circuit calculations that we might need to do. If you look at the circuit setup here, we have a series circuit involving a battery, an ammeter and a variable resistor, and they're connected using the black, the red and the blue wires. They're connecting that series circuit, and then we have two green wires connecting a voltmeter across the terminals of the battery. Now what's interesting here is if we then start with the variable resistor on its maximum value, we read 5.53 volts. As we reduce the resistance of the variable resistor, as we might expect on the ammeter on the right, we see the current in the circuit begin to increase as we reduce the circuit resistance. But the other thing we notice is that the voltmeter reading also reduces. So the voltmeter reading started about 5.5 volts when we were drawing very little current. As we draw more and more current from the battery, the voltage output of the battery appears to decrease. You can see now down to about just over 4 volts when we've got a current of 50 milliamps and 3 volts at 100 milliamps. And you can see there at 150 milliamps we're down to only 1.9 volts from our battery. If we increase the resistance to reduce the current again, the output from the battery voltage will increase again. So the first thing we need is to understand the reasons for that. So what we have here is a schematic diagram of that circuit that we've just seen set up. And what we've observed, what we've seen is that reducing the circuit resistance will cause a decrease in the voltmeter reading. Now we have to try and understand why that is. What we would expect here is that we've got a power supply of a certain EMF, let's say 5.5 volts in the circuit that we've just seen. Meaning that as each coulomb of charge comes through our battery here, it's picking up 5.5 joules of energy, which is then dissipating here in the circuit resistance. What we would perhaps expect to happen is that as we reduce the size of this circuit resistance, we've got the same voltage across it, 5.5 volts, but because the resistance is smaller, that's going to drive a larger current through it. So we would expect to see the ammeter reading increase because we're reducing the resistance of the circuit. So the 5.5 volts that we're putting across this resistance will drive more current through there. What we wouldn't perhaps expect to see is that the voltage output of our battery appears to actually decrease. So we need to try and understand what is the reason for that. Well, the reason for it is that the battery itself has an internal resistance. Now we can sometimes draw the internal resistance as a resistor there, label it R, lowercase r, indicating the internal resistance. We put a dotted line around there indicating that that internal resistance is actually internal to the battery itself. So the battery itself here has an internal resistance. There is some resistance to the passage of current actually through this cell pack itself. Now because there is some resistance there, we will actually need some voltage across that internal resistance to drive the current through there. So the voltage output, which we will generally call the terminal PD, the potential difference we measure across the terminals of our battery, which is really the potential difference across our external resistance. If we just connect a voltmeter across the battery terminals, we're actually measuring the PD here across this external resistance. That terminal PD will actually be a little bit less than the EMF of the cell because there are some volts across this internal resistance. So what we have here is that the EMF is equal to, if you like, the terminal PD. That's what I'm measuring with the voltmeter, the potential difference across this external circuit, this external resistance that we have here. That will be V, and that's what we're measuring on the voltmeter. But we're also getting some volts across this internal resistance. We sometimes call that the lost volts. Now we can calculate how many, we can't measure directly how many volts are across there, but we can calculate it if we know the current in the circuit. Okay, it'll be the current multiplied by the internal resistance there will give us what we can call the lost volts, the PD across the internal resistance. Now, clearly, As we reduce this external resistance and more current flows through this circuit, that will mean more current through the internal resistance. Now the size, although we reduce the external resistance, but the size of the internal resistance is unchanged. And therefore, more current in the circuit through that internal resistance will necessarily mean more volts across it, an increase in the lost volts. So we can say that here. The battery has an internal resistance. Reducing the external resistance will mean a greater current will flow in our circuit, and a greater current will flow from the power supply. A greater current will flow through the power supply. And because of that, then there will be more lost volts across the internal resistance, because clearly we need more volts across the internal resistance if we're to drive a larger current through that internal resistance. So it's a little bit like it is like a potential divider circuit that we looked at previously. Obviously, if this resistance decreases, but this resistance remains unchanged, okay, and the internal resistance is just in series with your external circuit resistance. So this resistance now is a larger proportion of the total circuit resistance. It's going to take a larger share of the EMF of your battery. Okay, this resistance reduces, but this stays the same. This is now a bigger proportion of the overall resistance. It's going to take a bigger share of the overall number of volts. Remember that whatever volts are across the internal resistance, you won't be able to measure with your voltmeter. Your voltmeter is only measuring the potential difference across the external resistance that you have connected to the terminals of your battery. Okay, suppose we have a battery with an internal resistance. We connect a voltmeter across the terminals of the battery, and we have a circuit here with an external variable resistor and an ammeter. Now, what we could do is we could change the setting on the variable resistance, and we could record a series of values here for the reading on the voltmeter and the current across the voltmeter. We get a series of values just by changing the variable resistance, recording the value of the voltage and the current, changing this setting again on the variable resistance, taking another pair of values. And we could plot that as a graph. Now the question is, what might we expect this graph to look like? Well, let's just think about how this circuit is going to split up the EMF of the supply. Okay, so the EMF, the supply, will be equal to the potential difference across our external circuit, what we often call the terminal PD. Okay, that's the terminal PD, is the potential difference that is measured by a voltmeter connected across, simply right across the terminals of the battery. The terminal PD will be less than the EMF because some of the volts of the supply will be across the internal resistance. Now we can't measure that directly with the voltmeter, so V here is the reading on the voltmeter. But what we could do is we could calculate that if we know the current in the circuit and we know the internal resistance, because the PD across that internal resistance will be the current in the circuit, then flows through that battery, multiplied by the size of the internal resistance. Yes, V equals IR. Now, if you think about it here, we are plotting the terminal PD V on the vertical axis of this graph, and we're plotting current on the horizontal axis. So we know that the general equation of a straight line graph is y equals mx plus c, where y is the quantity plotted on the vertical axis and x is the quantity plotted on the horizontal axis. So we've got V on the vertical axis, not the EMF, so I've got to rearrange this formula. And I can rearrange that by subtracting IR from both sides, and I can write that as that. So this here is just this formula rearranged to make V the subject, since it's V that we've got plotted as the y variable. So let's just show that here. So we've got V plotted as the y variable, plotting current on the x-axis. So what can we see here? Well, when we plot this then, by comparing our formula here to the equation of a straight line graph, what we would expect to do is to get a straight line, because the gradient of our graph will correspond to minus R, where R is the internal resistance, and the internal resistance does not change, it's a constant. So our gradient of our graph should be a constant, in other words it should be a straight line, but the gradient will be negative. So we should have a line that slopes down, and we should have a positive intercept on the vertical axis. You can see here plus E, which will correspond to the EMF of the battery. So in other words, our graph should look something like this, where here we've got the EMF of the battery on the vertical axis. So the EMF is the reading on the voltmeter when the current is zero. We've got zero current here flowing in our circuit. So basically, if we had a switch here and we opened it so there was no current flowing, if there was no current, that's when the voltmeter will read the EMF. Notice here we will have a maximum current that the battery can supply. So I max here, the maximum current, would be when the terminal PD is zero. So in other words, if I was to short circuit this battery, so have no resistance at all in here, just have a resistance, a connecting lead of negligible resistance connected between the terminals, in that situation, all of the EMF of the supply, all of the volts of the supply would be across the internal resistance. So basically, I max for a circuit with internal resistance can always be calculated by doing, well, we know that I is V over R. So if we've got the EMF all across the internal resistance, and the total voltage of our supply across the internal resistance, we've got no external resistance at all, then that will be when the current is maximum. So we can always work out, if we know the internal resistance, we can work out what the maximum current that supply could give. So if you like here, so just taking this formula here, terminal PD is current times external resistance, factorize that. The current in our circuit is always given by the EMF divided by the total resistance of our circuit. But if the external resistance goes to zero, maximum current that a supply can provide is the EMF of that supply divided by its internal resistance. So the current that can be drawn from a supply is limited by the internal resistance of that supply. The larger the internal resistance, the smaller the maximum current. So sometimes for a EHT power supply, a high voltage power supply, you deliberately on those supplies use a large internal resistance to limit the current they can supply for safety. Things like a car battery, which need to be able to provide very large currents, will need to have small internal resistances in order that they can provide that large current. So here we have a very good question to practice ideas behind internal resistance. It says the voltmeter reads 1.62 volts with the switch open and 1.45 volts with the switch closed. Determine the battery EMF and then its internal resistance. So the first thing we need to understand here is, why have we seen the reading on the voltmeter drop when we close this switch? Well, with the switch open, there is no current flowing in this circuit at all. No current flowing around the circuit. Now we know, if we're not told otherwise, there will be an internal resistance here. Okay, so that there, drawn in blue, that is a resistor, or a resistance that is internal to the battery itself. If no current at all is flowing in the circuit, which will be the case if we have that switch open, there will be no current through this internal resistance, and therefore there will be no volts across that internal resistance. Remember, V equals IR, so if current is zero essentially, and that resistance there, which typically might be half an ohm or something like that, then V will, or the lost volts there, will be zero. And the terminal PD, which is measured with the voltmeter, will be reading the EMF. That is the only circumstance that a voltmeter connected across the terminals of a battery pack will measure its EMF. The only circumstance is that when no current is flowing in that circuit. If you want to, I suppose you can think about it as a potential divider here. Our external resistance now is essentially infinite because of the huge resistance we've got here. Obviously we've got a non-conducting gap in the circuit, so essentially this external resistance is infinite. The internal resistance is tiny, so if you think about it as a potential divider, the whole of the volts of the battery will be across this external circuit. And so our voltmeter then here, essentially in this point, is measuring the EMF when that switch is open. So the first part, our answer to part A, is easy. The EMF of this battery is just 1.62 volts. So that is worth remembering. When no current is flowing in your circuit, a voltmeter connected across the terminals of a battery will in that circumstance will measure the EMF of your battery. Now then, what happens then here if we close the switch? Well, if we close the switch, what we see here, as we suspect, the voltmeter reading will drop, because as soon as we close that switch, current is flowing in our circuit, current flowing here from the positive terminal, conventional current flows round to the negative terminal. The current then will have to flow through the internal resistance, and therefore there will be some volts across that internal resistance, which we won't then get across our external circuit. So how could we go about doing that? Well, what we know here, if the voltmeter is reading 1.45 volts, we've got 1.45 volts across our 4.7 ohm resistor, so we can work out the current in that resistor. So I will equal V over R. We know that across our 4.7 ohm resistor, with the switch closed, we've got 1.45 volts. And therefore we can work out the current in our circuit, which will come to be 0.309 amps, to three significant figures. And what we can then say, right, okay, a current then of 0.309 amps is going to flow around this circuit. It'll flow through the external resistance, but then as it moves through the battery, it'll also flow through the internal resistance. Now, what is going to be the PD across the internal resistance? Well, we can work that out as well. PD across the internal resistance, well, an internal resistance is just a resistance that is in series with our external resistance. So they behave as a potential divider. If you put a voltage across two resistors in series, they will divide up that voltage between them, and they will split that voltage between them. So if we know that we've got 1.45 volts across the external circuit, we know the EMF of the battery is 1.62 volts, then the other 0.17 volts has to be across our internal resistance. Now we can then work out, of course, the size of the internal resistance, because that will just be the PD across that resistance divided by the current through it. We've just worked out we must have 0.17 volts across the internal resistance. The current through it is 0.309 amps. Whatever current flows through the external resistance has to pass through the internal as well. In this battery pack, we've got an internal resistance of 0.55 ohms. We have a question here on a relatively simple looking electrical circuit. The battery has an EMF of 6 volts. The voltmeter reads 5 volts. So straight away here we know that this circuit, the battery must have an internal resistance, because if it didn't, then the voltmeter here would read the same as the EMF. So the fact that the voltmeter, when connected across the terminals of the battery, is reading less than the EMF means that we have some lost volts. We have some volts across the internal resistance of the battery, hence the voltmeter reading is only 5 volts. We're told the variable resistance here in this situation is set to 10 ohms, and we need to work out how much energy is converted to thermal energy in the battery during 1 minute. And then later on, if the variable resistance is increased to 25 ohms, what will the new reading on the voltmeter be? Well, okay. So we know that this has an EMF of 6 volts. We know that in here somewhere we have got an internal resistance. So let's just put that on that circuit so we don't forget. Now the first question, how much energy is converted to thermal energy inside the battery? Well, why are we getting energy converted to thermal energy in the battery? And why is the battery going to get warm? Well, obviously as we drive a current here around the circuit and through the battery itself, current's going to flow here in this circuit, conventional current from positive to negative. As the current flows, the current passing through that internal resistance will cause heating. We'll get energy transfer in that resistance as the current passes through it. That energy, or the power transferred in that internal resistance, will be given by I squared R. Remember, power, electrical power, is VI or I squared R. So if we could work out the current that will flow in the circuit, and we could work out the internal resistance, we could work out the power dissipated in this internal resistance. So let's think, how are we going to do that? Well, if we know this resistance is 10 ohms when the voltmeter reads 5 volts, we can work out our current. We do an answer here to part A. What we know is that the current in our circuit is given by V over R. We've got 5 volts here. Voltmeter, don't forget, is reading the potential difference across the external resistance that we have connected to the circuit. The voltmeter never ever reads the potential difference across the internal resistance. It's always measuring the PD across the external circuit. So 5 volts over 10 ohms. We've got a 0.5 amp current here flowing from the power supply. Now we can work out the internal resistance, of course, because we know that if the EMF of the battery is 6 volts, 5 of those volts are across the external circuit. Presumably the other 1 volt, 6 minus 5 equals 1 volt, is across our internal resistance. And so, what that means, if we use R equals V over I, with V, PD now across the internal resistance, which is 1 volt, dividing by the current in our circuit. Of course, whatever current flows through the external circuit has to come through the internal circuit as well. So that's half an ohm. 1 volt divided by half an ohm means we have a 2 ohm internal resistance. P equals VI. Power equals power dissipated in a component is the potential difference across it multiplied by the current through it. But V is just IR. So IR times II squared R. 0.5 squared multiplied by 2 ohms then is half a watt. A watt is a joule per second. So every second we've got a half a joule of energy transferred from electrical energy to thermal energy in this resistance here. So in 1 minute, work done, power multiplied by time. So the energy transferred in 1 minute is the power, 0.5 watts, or 0.5 joules per second, multiplied by the number of seconds in a minute, which is 60. And so what we have is 30 joules. During 1 minute, 30 joules of electrical potential energy is converted into thermal energy in that internal resistance. And that's why our battery will start to get hot after a while, because of that energy transfer. So what about part B? Well, we've already worked out that our internal resistance is 2 ohms. Now then, if we increase the external resistance then to 25 ohms, what's the total circuit resistance going to be now? Well, it's going to be 27 ohms. So, the current that will flow in a circuit is the potential difference, the total PD, divided by the total resistance. Yes, V equals IR, so I equals V over R. We know in our circuit in total we've got a total voltage of 6 volts across a total resistance of 27 ohms. And so we can work out the current in our circuit. Yes, that's 6 volt EMF. Some of those volts are across the internal, some is going to be across the external. But if we're looking at a total circuit resistance of 27 ohms, the external plus the internal is 27 ohms. The total voltage across that is going to be 6 volts. And there we are, 0.222 amps. So what potential difference then will be across the external resistance? Well, again, we can use V equals I times R, but this time just on the external resistance. So let's put that here for the external resistance. V equals I times R. Just worked out the current in the circuit. If we just look at the external resistance, which we know is 25 ohms, to 2 significant figures, we will get 5.6 volts. So really, calculations like this, we just need to remember we've got, if it's a circuit with an internal resistance, we've got this resistance that we can't see inside the battery that we're going to call an internal resistance. And it behaves just like a series resistance, an extra resistance in series to our external resistance here.